Okay, so I guess we're gonna get started. I think I will get done well before the hour, but just in case there are questions. So the topic for today is multi-echo fMRI. I want to try to explain you what it is. I want to try to explain you a couple of things that you can do so you have multi-echo data. I apologize in advance because there are quite some formulas there, but it's the only way I feel I can really explain what we're doing with the data. And then during the last part of the talk, I'll try to show you some examples in which we've used multi-echo data either in our lab or in other places so you can see how it might apply to your own work. Of course, there is a lot more than what can be explained in just 1 hour. So this paper recently came out. It's a review by Prantik and Bandettini and other people who have worked quite a lot on multi-echo. So, if after the end of this hour you feel that this is something you want to bring to your own research, that might be a good place to go. You can, of course, send me an email or any other people in our group. Mostly all of us have the fun to work with multi-echo data at some point or another. Okay, so what is multi-echo? And let's try to think of what's our regular single echo data. So what we do in an experiment, we collect data over time. In fMRI, we're interested in fluctuations of the signal over time. And we set a TR, 1-2 seconds, depending on our experiment. And within that TR, what we're going to acquire is we were going to acquire a volume of data every TR. And we acquire volumes of data in terms of slides. So what we do is within that TR, we will acquire, following an excitation pulse, a series of slides, and then that will give us one volume. We do that every TR, and what we end up with in terms of the data is for every single voxel, we have a single time series of the evolution of this signal that we're measuring and that we know somehow is related to neuronal activation or something like that. With multi-echo fMRI, what we're going to do is instead of acquiring a single time series per voxel, what we're going to do is every time we're going to acquire more than one slice. Following up each excitation pulse, which is this red thing here, what we're going to do is acquire our data at different echo times, which is the distance between the excitation pulse and when we actually do our readout of the data. To think about it, the whole idea is we're going to acquire more than one time series, and those are going to have different weightings in terms of the signals that form whatever it is that we record, okay? So we do this over time, and the big difference is that instead of ending up with a single time series per voxel, we will end up with n time series per voxel. Usually 3, but nobody says that you cannot acquire 4 or 5 echoes depending on your experiment. We do this at no SAR cost because there are no more excitations, and we do this at a slightly loss in temporal resolution because to fit that third echo, so usually you're acquiring your data around this echo, so getting the first one comes for free because basically the scanner was just waiting to get to this point and acquire this data. Anything you acquire after that will come at a little cost in terms of temporal resolution, but nowadays with multiband, really is not going to change the TR that you have for your experiment. And that's one of the reasons why maybe multi-echo is starting to catch up more. And then maybe, you could think there is a slight loss in spatial resolution because if you make your boxes too small, then the latest echoes you may have no signal. But again, I wouldn't think that you're going to have a big loss by doing multi-echo. So this is multi-echo. Please don't confuse this with multiband, which is the other multi-term that you might be hearing a lot these days. Multiband means you acquire several slices contiguously. What allows you to do is to get more data at a shorter TR, okay? It doesn't give you these different time series with different weightings that we're going to try to exploit in order to separate noise from good signal and things like that. And you can have sequences, and they do exist, that they do both things, multi-echo and multiband. So, is that clear so far? Okay. So now we have 3 time series. So, if I were to focus on a given time point, what we have is 3 different images, and this for every single time point. The first thing, so here we have the images for the first echo, second echo, and the third echo, all of them kind of plotted on the same intensity. And we can see that the first echo tends to have a much more signal than the other ones. That doesn't mean per se that has better ball contrast, which is the thing that we really care about on fMRI, but at least it's a good thing to have signal, especially in places where maybe at the second echo or the third echo we don't have. Like for example, and think of the second echo as kind of what you would be doing should you be doing single echo fMRI, okay? That's the way we usually compare It's fair to do that because that second echo or middle echo tend to be the same echo time that you would use should you be acquiring just a single echo regular fMRI data set. So we start to see, and we'll look more into this, that by doing this, suddenly we have some other time series where we started to recover signal in places that we didn't have. And the reason for that is that even though when you do an fMRI experiment, you tend to set up your echo time to an optimal echo time, which is usually the T2 start of the tissue of interest, and we tend to go for 3 Tesla around 30 milliseconds. The truth is that the T2 star varies a lot across the brain. And there are areas where the T2 star, it's around 20, while there are areas on the back that might be around 40 and 50. So when we choose 30, for many reasons, we're going to be, having a compromise in which we lose signal up here. Because now we're doing another acquisition at an earlier echo, we are going to be able to recover some of the signal in these areas. Okay, so here is where I start with the formulas. Please follow with me. I'm going to try to explain them in an intuitive way, not all the math, so you can follow with me, because I think it's the only way to start understanding what we try to do with these signals that we have. So here we have a brain, and in a given set of 9 locations around here are the time series. And what we record in a given voxel at a given time point and for a given echo is given by this formula, okay? So the signal, this guy, at a given voxel, one of those locations, at a given time point, this is time, and for a given echo, you're looking just at one of them here, has 2 main components. Has a component that we call S0, that basically captures local fluctuations in T1 changes, hardware instabilities, the bad stuff, okay, the things we don't like. And then we have a second component of the signal that we call RT2 star that captures local fluctuations in field homogeneity. This includes what we're interested, the changes in the signal that are related to neuronal activation. It also includes a few other things, but overall, we definitely are interested in this part more than we're on this. And then noise, which is thermal noise and everything else that we haven't modeled. But overall, we could assume that at this point, this is mostly thermal noise. And the other thing we can do when we're looking at these 2 components for each of them, let's pick this guy, we can think of this as having a mean value across time and then a small fluctuation sitting on top of that mean value, okay? So we have S0 for a given voxel over time is equal to the mean value in that voxel of S0 plus a little fluctuation that sits on top of that mean value. And this is an assumption that we can do because through those fluctuations, as is the case here, they should be much smaller than the mean value, okay? You still follow me? Okay. And things that we might want to do is actually to try to, now that we have multi-echo data, before it was kind of hard when you just have one echo only, it's kind of, it's hard or sometimes impossible to separate these contributions. Because we have multi-echo data, I'm going to show you that we can do things to actually start separating and getting estimates of each of those things separately. Okay, so that's kind of the introduction of what it is, and now let's try to see what things we can do with this type of data. Some are things that you will actually want to do with your data, some are things that I'm just telling you for example purposes, but really there's not that much that you can do with that. Okay, so here is our original formula of what's the signal for a given voxel at a given moment in time and at a given echo time with the good part, the bad part. We start to see that the good part seems to not be dependent on the echo time. Here it's associated with the echo time, so that's a hint there. And for each of them, we can think of them as having a mean value and a small fluctuation sitting on top of that mean value, okay? The same for this one as it's for this one. This is the artifacts, kind of, I'm simplifying things, but just so you can follow me. And this is the good stuff, hopefully. The way we define things, because we said that, this is equal to the mean and something sitting on top of that mean, and this is equal to its mean and something sitting on top of that mean, these 2 guys, we can assume that they have a mean of 0, okay? It follows the way we have, and again, defined things. When we, based on those definitions, then if I were to look at the mean signal across time for each voxel at a given echo, which is basically this guy across time, given that these guys, their mean at 0, if you just separate those things, it simplifies to this. So basically the mean signal across time. So this is for those of you that are familiar with AFNI, that's a 3DT stat minus mean, and it will give you the mean across time. It's equal to the mean S0 signal multiplied by the exponential to the mean RT2 star and T. Because we have an exponential, it might seem a good idea to do the log of that. Once we have the log of that, this separates into this. Nothing has changed here. And here basically we have this comes down. So what we have in the exponential here after the logarithm comes here. And this guy, just because it's multiplying, becomes a summation. And if you look at this, basically this starts to look like a simple linear equation where we have that y, which is something we can measure on every voxel because it's just the mean of our time series across time for a given echo, equals something that is voxel dependent. This is the RT2 star mean multiplied by the echo time. We know the echo time because we set them on the scanner. We're going to do multi-echo with 3 echoes at 14 milliseconds, 27, and 42. So we know this. And another part here, that it's the logarithm of the mean S0 signal that we also don't know, but we might be interested because we have 3 echoes. We can set this system of linear equations where we know this, and we can try to solve for these two guys, okay? If we were to do that, we can get a spatial map of the average S0 for our time series and a spatial map of the average T2 star for this particular data set. Here you can start to see that, for example, this captures a lot of the intensity in homogeneity across the brain, with the areas closer to the coils having more signal than the areas in the middle. Here we can see some anatomical structure because the relaxation time for the ventricles is much larger than, for example, for the white matter. In fact, you can see, and for that I will refer you to the review paper that I saw at the beginning, some people claim that these T2 star maps can be a good surrogate to try to do the alignment from the functionals towards the anatomical, because they tend to have very good tissue contrast. I honestly haven't tried myself, so I cannot tell, but it's something that's recommended. Here, sometimes you will see I put these names. For those of you who have been working with Mica, which is one other application that you can do with multi-echo data that I will introduce in a little bit, these are the names of the files that Mica will give you that actually contain this type of information. Is this clear? Okay. So that gives us what I would call the static or the mean S0 maps and the T2 star map. Another thing that we might be interested is in actually obtaining an estimate of those fluctuation of S0 and fluctuations of R2 star across time. So how do we do that? Again, here is our original formulas, the formula for the signal at a given voxel at a given moment in time and echo, our definitions, working definitions of each of these two components based on their mean and a little fluctuation, and then we also agreed in the previous slide that should I look at the mean across time of this formula, basically it reduces to this, okay? So if I take this guy and introduce these two definitions, I get this. So basically I am substituting this by all this, and I am substituting this by all this. I mean, the purpose of doing this is not for you to write it down, but the talks are going to be online later, so hopefully if you want to really get to understand it, you can navigate through all this. So now once we do that, we can actually try to introduce this definition into here because it will help us. So basically for that, I separate these two things in this, multiplying by the exponential of everything else. And here I just taken this guy out and I have put a 1 and divided this guy by this guy, and this is what you see here. That way I get to extract all of this out of here, and this is what's left. So basically we have all the mean values here, and now the fluctuations separated in these two terms. Because it's really hard to do math with an exponential, and given that those fluctuations are small, the first approximation that we're going to do is to substitute this exponential term by the first order Taylor expansion, okay? So this is an approximation, so basically this goes away, and in its place we put this. When we do that, so this is the same, this is the same, and what you see here is the multiplication of this by this. So basically 1 by 1 gives you this one by this guy gives you this guy, this by 1 gives you this, and this by this gives you the big guy here, okay? This is a small fluctuation, this is a small fluctuation, this is a small thing multiplied by another small thing, so we can assume that all this is going to be much smaller than this and this. So again, just for the idea of simplifying things so we can work through the math, we can take that out, okay? Again, we are doing some assumptions that are to a given extent correct, and because we're doing assumptions and because the data is noisy, this is one of the things that I will ask you not to do with your data, okay? It's just for illustrative purposes. Now that we have this, we're going to define two things, just to put things in a unitless manner. So we're going to define something that we're going to call delta rho. That is just basically this. I'm just giving it a different name, okay? And we're going to define delta kappa. That is basically this guy, but multiplied by the average of all our echo times. This is just by definition. Why? Because this is the inverse of the T2 star, so this has units of seconds to -1. By multiplying it with something that has units of seconds, then it becomes unitless too. And it allows me to simplify this equation to something that starts to look again a little bit like a linear system. In fact, if I move this guy back here, and I could actually move this guy down here, actually, then we end up with something that again seems to be linear. A plus something that multiplies by the echo, and then plus the other thing that we're interested in solving, okay? So should we do that? Again, so here we have data for a few voxels in this area. What I'm plotting you here is the signal for those voxels across time for the middle echo, okay? The one that would be our single echo fMRI, assumingly. And I'm gonna apply the math that I did and separate it into signals. And I'm plotting you what that math will give me as the estimate of the delta R2 star and the estimate of the delta S naught. Okay, so what do we see here? So for example, we tend to know that in general, although it's not always the case, but if we were doing resting state or a block design, the slow drift that we see in our signals is an artifactual drift. That's why we tend to do a polynomial fitting at the beginning with Legendre polynomials or some sort of filtering to get rid of these really, really slow fluctuations. So what we can see is that by doing this math, in most of the voxels, the algorithm or the math tell us that the R2 star, which is the good signal, shouldn't include that drift. Again, it's not perfect, and as I said, this is something that, because of the amount of noise in the data, tends to give you really bad results. And here you have examples of some voxels where that didn't happen. But you know, in most of them, it seems that we're getting where we want. Now, the back component, the S node, in the majority of these voxels, we can see that actually was very good at capturing that drift. And it didn't do it that well here, and we could go into the reasons for that. But you know, overall it seems that things are working in the direction that we want. That makes sense? Another way to look at the quality of this data is again, for those of you who are familiar with AVNI, you can do Instacore on your data, which basically is for a given voxel in the brain, it computes you the correlation of every other voxel with that location. And so we do that with this original data I was showing you. We can see, you know, it seems some resemble of a network here, but not really. In fact, the last time I checked, networks don't tend to have horizontal or vertical stripes. So maybe this is kind of an artifact. If we were to do the same Instacore on the same location, but using our delta S naught, we would see that that tends to capture most of this artifact. And if we do the same thing on the delta R2 star, we start to look at a network that looks much better. But again, this is a noisy procedure, and you know, you can try, but I would do other things like what I'm going to explain next. Make sense so far? Okay. We can do even simpler things. We have 3 time series per voxel. Why not just combine them? All of those, at least the thermal noise, should be independent across them. So 3 measures, we combine them, we should get something better. And we can do the more naive way of combining them, which is just, you know, to sum them and dividing basically the mean. And some people have tried those things. But there are other ways in which we can get a better thought, let's say, weighting of those different time series as to optimize the contrast to noise, the bulk contrast to noise, which is what we want. And that's what we tend to call optimally combined. I'm not going to go into the details of how those weights are derived, but just think of them that this is something you can compute out of your data very easily. The Mica software includes the computation of this. If I think this is very easy to implement in AVNI, Daniel can tell us. But if you want a little program to do this, I can give you code. I have a little Python script that will just compute these guys and compute this estimate of a new time series that no longer depends on the echo time because it's the combination of the different time series. So you end up with something that you have a time series per its location. And this is what we tend to call the optimally combined time series. So this is an example of a given time point of a middle echo time series. And this is an example of a single time point on an optimally combined time series. And what you can start to see is that because we combine these three echoes, one of which actually had a lot of signal on those regions for which the middle echo didn't have, and because we've been kind of smart on how we combine them, we've been able to recover some signal in these areas that tend to have a lot of dropout in the regular single echo fMRI. If we were to look at this in terms of temporal signal to noise ratio, which is a proxy for how good my data is in a given voxel, we can also start to see just by doing this very simple approach, we're obtaining a gain on temporal signal to noise. This is not going to take care of artifacts in an informed manner, like the next thing I'm going to show you, but definitely we've taken care a little bit of the thermal noise, and we've also taken care of recovering signal in areas that had a lot of dropout. So it's not a bad starter for just a simple linear combination of the data. And then you end up with a single time series, and you move forward with your analysis, whether you want to do GLM, because this is an activity-based study, or functional connectivity and graph theory, whatever you want to do, you do it on this data, basically. Okay, so let's now look at the last thing, which is the echo time dependent analysis, which basically is what MICA, the noising, is based on, okay? All right, so we're going to think about what we're doing in a slightly different way for this. So again, same as before, here we have the signal that we record at a given voxel at a given time point for a given echo with its two parts, okay? Now, if we were to, at a given time point and a given voxel, let's say that, our S0 is this amount and our T2 star, which is basically the inverse of that, is this amount, because, that's the state of the brain, of that voxel of the brain at a given moment. If we were to plot the signal for the different echoes, so here on the x-axis we have echo time and here we have signal, we would see that the signal decays with this shape, okay? That's just what the math tells you. Let's imagine an instant later. Between now and that instant later, there's been neuronal activation. So neuronal activation should only induce a change on the T2 star. This wouldn't change and this would change. So we have a fluctuation that is of ball origin. If that was the case, we will have a second decay curve that looks like this. Okay, that's what the math tells us. Now, if we were to think of these things as the difference between them, we will get a curve like this. So this is just the difference between the two curves that I just showed you. Okay, and for those of you who have been looking to these things before, this looks like the ball contrast curve, where you can see that your optimal ball contrast tend to happen around your T2 star of the tissue, okay? Now, if instead of looking at this in terms of signal change, we now divide this by the mean signal value, it ends up looking like a line. So basically what this tells us is that fluctuations in our signals that are of ball origin, when we look at them in terms of signal percent change, well, signal change, basically the signal minus the mean divided by the mean, should show a linear dependence with echo time, okay? So we put that here. Now we can do the same game, but this time, instead of having from one moment to the next a change on the T2 star, having a change on the S0, okay? Let's say that you have your brain in a given state now, and then there is some artifact, something that is non-ball related. The two curves that you will get are like this. This is not exactly the same as this, but it's hard to think of the difference in terms of just looking at the two of them. If we do the different, it no longer looks like this, it looks like this. But if we do it in terms of signal percent change, we see a flat line. And this is the basis for the echo dependence analysis. The idea that signal changes that are of ball origin will show a linear dependence with echo time, and signal changes that are not of ball origin will show a flat dependence with echo time. Okay, and we're going to exploit this principle for doing some more advanced things. That makes sense? Okay. So Here we have a multi-echo data set. Basically, we have data at 3 different echoes, and let's say for a given voxel, here are the 3 time series. We've acquired multi-echo data, which I believe in all the scanners that we have here at the NIH, that's possible. I don't know if all of them have multi-echo, multiband, but I think so. But definitely multi-echo. And now we have a physical model of how fluctuations of those signals should behave as a function of echo time. Should they be things that we're initially interested on, ball-like fluctuations, and things that we would like to remove from our data, non-ball-like. So what can we do? Well, we could say, okay, so I have my data, this is a block design. So a candidate signal, because I know the structure of my blocks, this was a block design with 20 seconds on, 40 seconds off, 5 blocks, I can create this regressor that you usually use in your GLM. But instead of doing that, I can say, okay, I'm gonna fit this guy to each of the different echoes. If the fit, which gives me somehow a measure of how much the size of that fluctuation is, follows this model, that means that this fluctuation is present on this data in a model that tells me it's ball-like, it's something good. If this signal appear with this profile, then it would tell me that maybe what I'm seeing is not due to activation, but maybe due to the head moving in synchrony with the task, okay? So what we can do is actually, instead of doing that for a single voxel, we can try to fit this to the time series of every single voxel for the 3 echoes. Then once we do that, for each voxel, we have the 3 values of how big that signal appears. We can actually try to fit this model, and we can get an F statistic on something that tells me how good this linear model actually fits the data in a given location. This starts to look like maybe this was a visual block design experiment, and we can see that, it seems that here in the back of the brain, this seems to fit the data in this manner pretty well. But we don't know, so we can also try to do the same thing for the other model, kind of look worse, but again, we cannot just take decision based on look better or look worse, so we can kind of somehow come with a single number that tells me how much things overall look like this, or how much things looks overall like this, and that's what's called the kappa and the rho in the MICA framework. This was defined within that framework. So kappa is basically gonna be a weighted summation across the brain of this map multiplied by the intensity of the signal in one of the echoes or in the optimally combined. The idea being, if I just do the weighted average of all these, yeah, it works very well here, but it works very bad here. It's just want to wash out. So I just want to do a kind of a little bit smarter weighted average in which where the signal is present, I want to see whether in those locations it behaves like this mostly or like this mostly, okay? And that's going to be our kappa. Our kappa is going to be how much it behaves like this, how much this seems to be a ball-like or a good fluctuation. And our rho is going to be an estimate, a single number that tells me how much I look like this. So in this particular case, it looks like the kappa is much bigger than the rho, so I would end up kind of saying that most likely this is a fluctuation that is of ball origin. Does that make sense?
Sorry, in plus 2 and 3, yellow is high, right?
Yeah. Okay, so, it's not always that we're going to have a candidate like this, especially if we're doing resting states, so what signals do I go looking for? So one way to do that, and that's bring me to MICA, which is basically this combined with ICA, is to say, okay, I have my multi-echo data because I acquired it that way. If I didn't, then you cannot do this. There are many other things you can do to denoise your data in automatic ways. We have this physical model that we've learned that that's how things should work. And we can do ICA in our data, and ICA basically is going to take the data and tell me here are a series of signals that are present in the data with these spatial maps. Okay, that's what ICA does for you. It's a very common thing to do with resting state data. And we can apply to each of those components for which we have a map and which have a time series. We can do the same thing I just did for you as an example with the block design. So this is one component that was given by an ICA. We can try to fit that component in each voxel to each of the echoes. Those are the maps you get. Then for each of them, you can get the F maps of how much, it looks like this for the R2 star, or how much it looks like this for the F naught. And then by multiplying these guys by the actual spatial map, we can get a single value, this summary kappa or rho, that tells me whether this fluctuation overall tends to appear as being ball-like or non-ball-like. So in this particular case, when you do the math, it seems to have a very high kappa and a very low rho. So it tells me this is something that I might want to keep in my data. It's ball-like. It's good news because when we look at the spatial maps of how this signal appear, they kind of resemble some resting state network. You know, it's mostly constraints to gray matter. So it looks good. It seems to make sense. If we were to take another time series that looks like most likely noise, and we do the same business, we see that it looks like this. It tends to fit only on the borders. I mean, that starts to tell me that this is a bad component, but that's not what the algorithm takes the decision on. We do the same thing. We see how this, for each voxel, this behaves like this. This gives me an F map, or like this gives me the other F map, and then we average this weighted average by the actual map of the component, and we can see that for something like this, the rho is much higher than the kappa. So it looks like this kind of tends to look like it's gonna be bad. Okay, so Prantik spent a lot of time doing this. Okay, so before I go into that, when you do an ICA, your components are given back to you sorted by how much variance they explain. And you know, we know that big artifacts tend to have a lot of variance, but that's not enough to really take a decision because there are some signals of interest that also explain variance. If we were to take our components just the way they are produced by the ICA algorithm, and I were to plot their kappa, we can clearly see there is not a clear relationship between variance, which is the sorting, and how good you are according to the kappa. But we can take our components and resort them in terms of the kappa, and then we start to see that there is this kind of elbow behavior where we tend to have a few components at the beginning that they have kind of high kappa, these big guys here, and then there is the other part of the elbow after the shoulder there, where we see there are the remaining of components that they tend to have very low kappa. When we go back to the actual components and look at them, what Prantik and other people in the group realize is that these guys, they tend to look like what we see as the good networks that we tend to see on our resting state analysis. They also saw that should we do this in many different subjects, you always tend to have this behavior. Of course, the elbow doesn't fall exactly in the same place. The elbow is not as clear in all cases, but there is always this profile of having a few components or a number of components that have high kappa, and that they look like things that should be good. And then a series of other components that have definitely a very low kappa and appear after the elbow. You can do the same the other way around with the rho. And again, you can see that some of the component with a higher rho, there is also this kind of elbow behavior, and that these guys, the guys with a high rho, tend to look very clearly like artifacts. Not only that, but also should I sort the components based on the kappa, it's very reassuring to see that in general, those guys who have a very high kappa tend to have a very low rho. And it's these guys with a low kappa that tend to have a high rho. So they seem to separate, okay? But not perfect, okay? So this is good news, but then when you start using it, you realize it's not such an easy black or white decision, okay? And the truth is that ICA gives you components based on spatial independent. It doesn't have any information a priori that tells him, hey, you should give me components that are purely of one type or another. What it tells you is that overall, it tends to do that. It tends to give you components that tend to be purely ball and components that tend to be purely bad, but there will be a few of them in which might not be that easy to take that decision. That makes sense? Okay, so what I'm gonna do next is kind of walk you a little bit through what the Mica software or suite of tools does, which is just based on what I explained. This keeps changing quite often. So for the latest how it does it, please ask Prantik. But I hope this will give you a little bit of the background on, what are the different parts of it, and that way you can get a little bit more informed users. So we're gonna start with multi-echo data. If we don't have multi-echo data, we cannot do this. So what means we have data for different voxels. Those are time series and different echoes. We're gonna do some pre-processing, not that much. We're definitely gonna do some slice timing correction, some head motion, maybe registration to anatomical. I think lately Prantik recommends not doing filtering or smoothing. So it's basically a very minimal pre-processing that you're gonna do. Is that the optimal way to do it? I don't have an answer, okay? Then the next thing that the software is going to do is to compute that optimal combination, that weighted average in which we're using the smart weights, not just the mean, but the ones that allow us to optimize the contrast to noise. So now we no longer have 3 echoes, we just have 1, because when they optimally combine, we just compress the echoes. The first thing it's going to do is a PCA analysis, because this data contains signal but also contains random noise, and it's a good idea to get rid of the random noise before you do the ICA. So, and I'll go a little bit into that detail, but the first thing that it does a PCA analysis and selects some of the components and reconstruct the data, and is based on that reconstructed optimally combined data with not all of the PCA components that then it runs an independent component analysis. And then of that independent component analysis, it's also going to do a selection of components, and it's going to give you what is called the denoise time series. And then is this denoise time series which you can do your analysis. So if you have multi-echo data, and this is how we tend to do it when we're evaluating methods, you can pick your middle echo, or whatever echo is the one that looks more like the one you would have done, and do your regular analysis, and just plug it in here and get your results. If you want to just do the simple thing, you can get the optimally combined, just get up to here and just take it out of the pipeline and go here and do your analysis, your activations, your functional connectivity. Or if you want to go through doing all this, which is going to lead you to a much cleaner data, then this is what you take as input to the rest of your analysis. Okay, there are 3 options. The better the noise, the more work you have to put to it, a little bit less the noise. But in my opinion, as long as you don't have very precise constraints on spatial or temporal resolution, like really, really big constraints, I think there is no loss by getting multi-echo data and at least getting here. You're going to have an improving TSNR, and you're going to recover signal in those areas of dropout. Then if you have the time and the energy, you can go for this, which I recommend it too. But you know, I don't see that much loss by actually acquiring this richer data. Okay, so let's try to get a little bit into a few of these boxes. So here is going to do a PCA decomposition. For the PCA components, it's going to characterize them, but not only in terms of the variance, because just the variance, as I said, it's not always the best criteria here. So it's going to characterize them in terms of the kappa and the rho, and things that either have a high kappa or a high rho. At this point, we're just going to keep signal. So I don't care whether it's good or bad. Everything that has high kappa or rho, it's going to keep it, it's going to put it again together, and that's going to be the input to the ICA, where it's going to do an ICA decomposition for all the components that come out. It's going to compute the kappa, the rho, and 1,000 other things. Not 1,000, but a few more. And then it's going to do component selection based on that to give you the denoise time series. So for the part of the PCA does a decomposition based on orthogonality, and a regular PCA would basically keep components up to explaining a given amount of variance. The way Mica does it is it keeps components that are signal, meaning they have a big rho or a big kappa. And what that means is that they sit to the right, the left of the elbow, and that's all I can tell. How strict you are with where the elbow is, you can kind of play with that by passing these 2 parameters to the Mica software, but in general, I would say just go for the default values. And then during the Mica, what it does a second decomposition of the data, which is based on ICA, and then for each of the components, it's going to calculate a series of metrics. It's going to look at the variance plane, it's going to look at the kappa and the rho, how ball-like this component is, how non-ball-like this component is. But then in a kind of empirical way, I guess, Prantic decided that, you know, having more features might help with this classification, because as I said, some cases are very clear, but there are other places that it's not that clear whether you would put it. So the software looks at other things like the number of voxels that significantly fit the flat model, the number of voxels that significantly fit the linear model, the spatial overlap between the ICA map and each of the models, and a few other things. For that, unfortunately, there are a few references that I would recommend, and also the one of 2017, but the only way to get all the details is to go to the code, which is in Python, so you know it's open source, you can look at it. And then based on all these criteria, what the software does, it divides the components in 4 groups. One that's called accepted, those are the guys that are very sure good. The rejected, those are the guys that are for sure bad, and then 2 groups that are kind of there. And the way the software works is that anything that is on the accepted or ignored is kept on the data, and the things that get removed during the denoising are the things that are marked as rejected or mid-K. Okay? So, in case you're gonna use the software, just a few words on what's the inputs and what the outputs are. The software, it's at least until now, but Daniel, feel free to say if I'm wrong. It gets distributed by AFNI, but I think it's not the latest version. So if you really want to get the latest version, it might be a good idea to actually download it from the big bucket that Prantik keeps updating. And there are different versions in there. I think as of today is 3.1 or 3.2, the latest one. So as input, the minimum you can give to the MICA is, the fMRI dataset for all your echoes and the echo times. You have to write these ones down when you're at the scanner. So you want to do some of the pre-processing in a given way that was optimized, assumingly, for this type of analysis. You can also provide the anatomical, some pre-processing options, and some of these other parameters that I told you that in case you don't want to use the defaults. And this is because the MICA software as it's distributed has 2 parts. It has a program called mica.py, whose idea is that you give it this and it just does everything for you. It has a specific way of pre-processing the data, and it will do the alignment to the anatomical, and it will do and then at the end it will do the echo dependence analysis and give you the optimally combined under the noise time series. Or if you have your own thoughts about how would you want to do the pre-processing, you can jump directly into a subprogram called tedana.py that does that echo dependent analysis. You basically give it your pre-processed echoes, and it will run the PCA, the ICA, do the component selection, and give you the optimally combined under the noise time series. In terms of the outputs, it's going to give you the static T2 star map, the static SNOT maps, the things we computed at the beginning of the talk. It's going to give you the optimally combined time series. It's going to give you the denoise time series after the PCA and also after the ICA. It's going to give you the beta or the component maps for each of the components of the ICA. It's going to give you a dataset that only includes the accepted components, so you can go through them to see if it makes sense. It's going to give you the time series for the PCA components, the time series for the ICA components, and a lot of things of interest. This is something that you can ignore and just take the denoise and keep moving. I don't think it's a good idea. I think in fMRI data, a lot of things can go wrong. So if the software provides you with all this information, is so you look at it and you can take an informed decision of whether that denoising actually works or not. I understand that's a pain if you have 300 subjects, and that's a balance. You'll have to put a couple of automatic QAs that you have to check, but you have a few, like 10 or 20, I think it's a good idea to go through all this. So at the SFIM, what we generated in the past is a little tool that allows you to navigate in a kind of a little bit more easy and fast manner all this information. So we have an extra tool that you can run after MICA called MICA Report that will generate these web-based reports where you can see maps of your TSNR for the middle echo, the optimally combined and the denoise. You can also get that information that is on the different text files, like what are the components that got accepted, rejected, the ones that were put in the different groups, and the variance explained. And a few plots, it will come up in a second, where you can see the distribution of your components. Here we have on the left a scatter plot of the kappas versus the raw. So we can see that the accepted components tends to be here, because accepted are circles, and they have high kappa and low raw. The bad ones tend to be here, and the difficult here. So maybe we see a red triangle here, we know something went wrong. And then we can go for each of the components. We can see it's a spatial map, it's a time series, and it's a spectrum. And we have them listed in such a way that we can look at all the ones that were accepted, all the ones that were rejected, and we can see if something went wrong. If something went wrong, then we can decide to correct it manually, or we can decide to live with it. But I would definitely, if you see something went wrong, like it misclassifies something that looks like noise and accepted it, but the variant explained is minimal, it's no point, it's not going to change anything. But if, for example, you have a task design and you see that a component that looks like your task and has a very high kappa got rejected, maybe because it explains too much variance, and one of the criteria was the variance, that is something you need to correct, because otherwise you will be moving forward without your actual task information in there. And now, in the little time that we have, any questions? I'm just going to walk you through a few studies that have used MICA. So this is a study by Prantic in which they applied this procedure to clean up data to animal data on a 11.7 scanner with a very fine spatial resolution. This is just to make the point that nothing that I've explained makes assumption about, which field strength you're using, or whether this is animal or human data. For example, there are algorithms you can denoise your single echo data with ICA, and there are things out there that will try to automatically classify components as noise or not noise, but this might be already tuned to work with human data because they look for spatial patterns around the brain or things like that. Here, there is no such assumption, so you can take the algorithms and apply it to animal data. The same about with different field intensity, and here you seem to get much cleaner maps for the components than when you do single echo. One big advantage of having this informed way of deciding what's an artifact and what's not, and by informed I mean based on the physics, is that we can now try to separate slow drifts that are of a ball origin from slow drifts that are artifactual. And as a proof of concept, Jennifer Evans did this study a couple of years ago in which she played with 3 different types of experimental designs in a visual stimulation paradigm. Here you have your typical paradigm of different intensities but with very short blocks, and the reason we tend to do short blocks in block designs partly because of that. If they were too long, we wouldn't know how to separate that from the drift. But she also played with 2 other designs, one in which she has these very long steady blocks of stimulation over 100 seconds, so longer than a minute or maybe even a minute and a half, and this one that looks like a graded stimulation but also very long. So here what we have is the signal for the 2 experiments in a voxel in visual cortex just by looking at the signal after a little bit of preprocessing. Here we could maybe argue that we can see this in the this is in the optimally combined. Here there is no way to know whether this voxel was responding like this. If we do the trending, but the trending meaning trying to fit polynomials with 0 information of whether we should be fitting them or not, something that looks like this, which the polynomials, if we're not using too high of an order, are not going to fit, still remains, but something like this is just going to be gone, because it's just going to fit one of those polynomials and you just took it out of your data. But if you do the MICA denoising, what you can see is that MICA decides in a quite good manner that things that are ball-like contain this square-like fluctuation, and even this one that is graded, and it was able to separate them from the actual drift that makes them impossible to kind of visualize here. So this is part of what would end up on the rejected and mid-K, and this is what you see when you combine what's the accepted and the ignore. And what that translates in terms of activity is that if we were to try to get activation maps, just looking at the optimally combines, we will get nothing. With the detrending, we will get something for the square experimental paradigm, but nothing here. And with the denoise time series, because it's able to separate things, we would see the activation for both type of paradigms, and would see nothing on the non-ball part. Another case in which you can use this is, for example, if you're doing cardiac-gated fMRI. So cardiac-gated fMRI, it's one option that people use sometimes when you are interested in the brainstem, because it has a lot of pulsatility artifacts. So instead of just acquiring your data at regular TRs and having that structure at different positions because of the pulsatility, you decide to acquire your data synchronized with the cardiac cycle. So that way, even though this thing is moving, because you always image it in the same moment relative to the cardiac cycle, you get it on the same place. Now, because your TR is not constant, you're introducing some fluctuations on the baseline signal of your data that are non-ball, but are going to really kill how you can look at things, because you'll have this fluctuation mixed with the ones of interest. But these fluctuations are clearly non-ball. So when we run MICA on this type of data, what we see is that we always find a component which really, really high raw compared to everything else that captures very well these fluctuations. Their associated component seems to look like a kind of almost like an anatomical map. But the important thing is that we did it, I don't remember, 10 subjects, something like that. And it always captures very reliably with a very high kappa, so it always put it on the wrong side of things and removes that. And because it does that, what we can see here is that both in terms of activation extent and in terms of statistics, it gives us a boost compared to either the middle echo or something like the optimally combined. The reason why the optimally combined wouldn't work in a case like this is because that non-constant signal is affecting all the echoes equally. I mean, that's why it's a non-ball, so it's there. When I do the average, no matter how informed it is, that signal is still present. I'm not taking it out. So in a case like this, optimally combined doesn't help. But MICA, which separates things according to whether they're artifact or not, really gives you that boost. We also tested MICA with task data for different tasks. And this was event-related design with motor tasks, some different visual tasks, reading tasks, and the take-home message is basically for all the tasks in terms of activation extent and T statistic, MICA always did better than either using just the middle echo or the optimally combined. So you tend to get a gain. And then, as I said, you can find out there sequences that combine multi-echo and multiband, and they seem to work quite well. There is this study by Olafsson in which they show that actually when you do that, you capture some artifacts that are specific to the multiband, and also because of the gain in temporal resolution and the gain on not having that much aliasing of some high-frequency artifacts into lower frequencies, for all the subjects, by doing this, the number of components, of good components, in a multi-echo multiband sequence seems to be always higher than the number of components on a simply multi-echo sequence. Now, how to interpret this or whether this is the real answer of how the brain works or this one, I don't know. So, conclusions. Multi-echo allows you to capture additional information with minimal cost in terms of temporal and spatial resolution, so why not? That additional information is not just additional information that we cannot use, but it seems to be pretty useful. You can increase CNR in dropout regions just by simply doing an optimal combination of the echoes, or you can really improve the quality of your data and the power of your analysis by doing something like MICA. But MICA is something that it's very promising, but it's still in the making. It will not clean every artifact, not because you run MICA on your data, you can say this is artifact free, that's whatever I get is the ground truth to everything. No, it's just another way of hopefully removing more of the artifacts in your data and getting to extract more meaningful information out of it. It's still under development. It can definitely improve the quality of your data. And just for you to look at this is just a video of the data as it comes out of the scanner. This is a video of the good components and the bad components, and you can see how when things work well, which is most of the time, you can just even almost look at this raw time series and see the evolution of the different components. So that's all I had. So thank you very much, and if you have any questions, please. I think you're supposed to grab the microphone for the videos, but please go ahead.
You mentioned
The microphone. If it works.
Okay. Well,
it's okay. Don't worry.
Okay. You mentioned at least 3 echoes are needed for the MICA to work. So there are more echoes.
No, I didn't say at least. I mean, think about it. Most of the times you're doing fits, so you can do a fit to align with 2 points, but 3 seems better than 2. 4 seems better than 3. 5 seems better, blah, blah, blah. But what you have to also keep in mind is that the later echoes will have almost no signal. At some point, you'll run out of signal. So it's a balance. So it really depends how fast you can image, how close you can put your echoes. That's what will give you the answer. I think that 4 or 5 are easy to fit usually, and you still have signal. And I think you can do much better than with just 3. Yep.
Does this give you a sensor list that you can use in your regression?
Who gives you that?
Does it provide
Mica? Not that I know of. Maybe the latest version includes something like that. No. I mean, and maybe I'm wrong here, but you're kind of removing components as a whole or not. So it's not like you're censoring parts of a time series, just a whole time series goes out or doesn't. But maybe the new version does some combination of things that I'm not aware. No, not that I am aware of. Thank you. Oh, go ahead.
Sorry.
Yeah.
And I apologize if this is something we already talked about. Could you talk about what the PCA adds that the ICA wouldn't?
So the PCA tries to separate random noise from signal. So that's why the first step is a PCA in which you basically pick everything that you think is signal, but signal as good or bad signal. So one way to do that, usually when you do a PCA, in terms of the variance, it looks like this, and the last part tends to be just random noise. The way the algorithm does it is it picks a signal, everything that has a high kappa or a high rho. I don't care whether it's good or bad, I'm just gonna keep signal. Because that helps with convergence in the later step of ICA. That's the reason.
But the fact that they're like, that the principal components have to be orthogonal to each other, there's no like neural basis for that, right?
No.
So,
I mean, there are studies that show, but again, you then put them back together. So you're just getting rid of that tail, which hopefully is just noise. You put them back together.
So you might expect that the ones that would identify those are the
Yeah, exactly.
So what exactly happens in that convergence of the ICA?
I am not an expert on fast ICA. I will have to refer you to that. But basically, I mean, what the algorithm is attempting to do this separation of the data into spatially independent components is just an optimization. It's basically, it will have a cost function about how good it's doing at that given point. And when you get it to converge below a given threshold that you can actually modify in the Mica, but I don't recommend it because basically you would be stopping the algorithm before it has actually converged. Then it says I'm done and it gives you the components. It's non-deterministic, and that's why you may run it once and it doesn't converge. You may run it twice and it does converge. It just gets initialized differently and it finds it's just an optimization problem. Thank you.